Hi everyone, this is Saiteja from CSC AML section B. Today my topic is about the memoryless property of exponential distribution. Let's get into the topic. Introduction. In probability and statistics, memorylessness is a property of certain probability distributions. It usually refers to the cases when the distribution of a waiting time until a certain event does not depend on how much time has elapsed already. To model a memoryless situation accurately, we must constantly forget which state the system is in. The probabilities would not be influenced by the history of the process. Only two kinds of distributions are memorylessness. Geometric distribution of non-negative integers, the exponential distribution of non-negative real numbers. A small introduction about this memorylessness property. It refers the case when it is about the calculating the waiting time. Waiting time of the certain event and depends on how much time has elapsed already. It is calculating. It is totally calculating about the time how the uh, time will be calculated and the what are the waiting time and the accurate assumed time when the how much time has elapsed in the depends on the model of memoryless situations with memory. Most phenomena are not memoryless, which means that observers will obtain information about them over time. For example, suppose that X is a random variable, the lifetime of a car engine expressed in terms of number of miles driven until the engine breaks down. It is easier based on our intention that an engine which has already been driven for 3 lakh miles will have a much lower X than would be a second equivalent engine, which has only been driven for 1,000 miles. Hence, this random variable would not have the memorylessness property. We can see the small example of a car engine. It expressed in terms of number of miles. The term used as number of miles driven until the engines break down. Calculating until the engines break down, it is clear based on our intention. The car engine has already driven 3 lakh miles. Will have the much lower X than would be a second. We can see the two engines of a car. One is already driven for a 3 lakh miles. As we compare to second engine, it is only driven for 1,000 miles. And we have to express the number of miles driven until the engines break down. Hence, this random variable would not have the memorylessness property. Here is another without memory. In contrast, let us examine a situation which would exhibit memorylessness. Imagine a long hallway lined on one wall with thousands of shapes. Each has a dial with 500 positions and each has been assigned an opening positions at random. Imagine that an eccentric person walks down the hallway, stopping once at each safe to make a single random attempt to open it. In this case, we might define a random variable x as the lifetime of their search. Expressed in terms of random of attempts the person must take until they successfully opened a safe. In this case, E of x is a is always been equal to the value of 500, regardless of how much attempts have already been made. Each new attempt has 1 by 500 chance of succeeding. So the person is likely to open exactly one safe sometime in next 500 attempts, but with each new failure, they make no progress towards the ultimate succeeding. Expectation of sorry. will always be equal to the value of the given of dial with the 500 positions. Discrete memorylessness. Suppose X is a discrete random variable whose values lie in the set 0, 1, 2, and so on. The probability distribution of X is memoryless preciously if for any m and n in 0, 1, 2 row, we have a formula called probability of x greater than m plus n by x greater than equal to m. That is equal to probability of x greater than m. There is a This is a formula for the discrete memorylessness when the for a m and n in a given values lies in the set of 0, 1, 2, and so on. A common misunderstanding memorylessness of a probability distribution of a number of failures x before the first succeed means, for example, if x greater than 40 by x greater than equal to 30, that is equal to p of x greater than 10. Continuous memorylessness. Suppose x is a continuous random variable whose values lies in the non-negative real numbers 0 to infinity. The probability distribution of x is a memorylessness preciously if for any non-negative real numbers t and s, we have probability of x greater than t plus s by x greater than t, that is equal to probability of x greater than s. As we compare this formula, we can see that a probability of x greater than t plus s by probability of x greater than t. We can see the probability of x greater than t will be cancelled, and the leftover the formula is probability of x greater than s is the continuous memorylessness is the probability distribution of x in the memorylessness precisely if for any non-negative real number t and s, we have the formula called p, probability of x greater than s. Exponential distribution. In probability theorem and statistics, the exponential distribution is a continuous probability distribution that often concerns the amount of time until some specific event happens. It is a process in which events happen continuously and independently at a constant average rate. The exponential distribution has the key property of being memoryless. The exponential random variable can be either more small values or favor larger values. For example, the amount of memory spent by the customer on one trip to the supermarket follows an exponential distribution. The exponential distribution has a key property of being memorylessness. The exponential random variable can be either more small values or favor larger variables. Exponential distribution formula. We can see the continuous random variable says x is said to be an exponential distribution if it has the following probability density function f of x equal to lambda into e power minus lambda x, whereas x greater than 0 because we have calculating the time complexity. Calculating the time is always positive, and we can only calculate the present time. We cannot move back to the time because time is always positive. It is a clockwise direction. It will be rotating, so we can see x greater than 0 always. Here is the formula for exponential distribution is lambda into e power minus lambda x, where lambda is the distribution rate. Exponential distribution graph. It shows the graph about the exponential distribution for several values of lambda. When we see if the lambda equal to 2,
The, the diagram will be the line will be shows in a dark way. When lambda equal to 1, it shows a little dotty way. As we compared lambda equal to 1 by 2, it will shows small dots in a small dots imaginary line way. We can see there will be a lot of difference when we compare. As the lambda value changes, the graph also changes. We can see through the graph which on the screen. We can observe the graph. We can see the horizontal. We have taken the f of x and the vertical. Sorry, we can in the horizontal we can see the x and the vertical we can see f of x of x. In this, it shows the graph exponential distribution for several values of lambda. If the lambda equal to 2, the graph will be like a arc, and we can see if the lambda equal to 1, the graph shows as a little darker, a little daughter way, and it will be some difference. It will show some different variation to before lambda value. As we can again distributed the lambda into 1 by 2, it shows a lot of different to compare to both lambda values. Shows in a small dot way. Exponential distribution applications. One of the widely used continuous distribution is the exponential distribution. It helps to determine the time elapsed between the events. It is used in range of applications such as reliability theory, querying theory, physics, and so on. Some of the fields that are modeled by the exponential distribution are as follows. Exponential distribution helps to find the distance between the mutations on a DNA strand, calculating the time until the radioactive particle delays, and also helps on finding the height of the different molecules in a gas at the stable temperature and pressure in a uniform gravitational field. These are the few applications as I took from the source. These are the I think these are the some of important applications. The exponential distribution helps to find the distance between mutations on a DNA strand. Exponential distribution mainly helps in finding the distance between mutation strand and also calculating the time until the radioactive particles delays, and also finding the height of the different molecules in a gas at a stable temperature and pressure in a uniform gravitational field. These are the few exponential distribution applications where we can use this application of exponential distribution to calculate the time and also distance and also height. These are the few applications. The memoryless property. The memoryless property tells us about the conditional behavior of exponential random variable. It's one of our key results which we will use in deriving the solution of querying systems that x be the exponential distributed with parameter lambda. Suppose we know that probability of x greater than t. What is the probability that x is also greater than some values of x plus t, s plus t? That is, we want to know if probability of x greater than s plus t by x greater than t, then the value will be probability of x greater than s. We can observe that probability of x greater than t will be cancelled, and the remaining will be probability of x greater than s. Discrete memorylessness. The only memorylessness discrete probability distribution are the ge- geometric distributions, which count the number of independent identical distributed Bernoulli's trials needed to get one success. In other words, these are the distributions of waiting time in a Bernoulli's process. Exponential random variable. It turns out the conditional probability does not depend on the probability of an exponential random variable. Exceeding the value is a value s plus t given t is the same as the variable originally exceeding the value s. Regardless of t, in our job example, the probability that a job runs for one additional hour is the same as probability that it runs for 1 hour originally. Regardless of how long it has been running, the exponential distribution is memoryless because the past has no bearing on its further behavior. Every instant is like the beginning of a new random period, which has the same distribution regardless of how much time has already elapsed. Implications of the memoryless property. The memoryless property makes it easy to reason about the average behavior of exponential distribution items in querying systems. Suppose we are observing a stream of events with exponential distributed interval times. Because of the memoryless property, the expected time until the next event is always lambda. No matter how long we have been waiting for a new arrival to occur, this behavior is a bit counterintuitive. We might expect that arrivals get more likely the longer we wait. For example, if the bus is supposed to come every 10 minutes and we have been waiting for 9 minutes without seeing a bus, we expect that the bus should be long very soon. There is the implications on the memorylessness property. Thank you all.